begin.
Okay, so thanks for being with me again, those who survived and had enough patience. So I don't need to introduce the, at least the title and the co-authors once more. But let me, as I said before we started recording, quickly recap what happened last week. So we know what the well, at first we had a look at a special instance of nuclear of a nucleus on Boolean algebra, which you can always obtain by fixing your favorite element or some chosen element of the algebra and forming a join with it. And we recall the axioms of nuclei, which is that they are inflationary, idempotent, and they distribute over conjunction or mid. But then we realized that Boolean algebras are a kindergarten setting for nuclei because, in fact, those simple operations of forming a join with a fixed element of the algebra for a given algebra, all the nuclei that there are. And of course, there would be other ways of describing the same operation in the Boolean setting because so many connectives are interdefinable. So we could instead say that given a fixed element, we and given an argument, another element of the algebra, we simply form an implication whose antecedent is this fixed element of the algebra. And of course, this is in the Boolean setting equivalent idea because it's just like forming the closed nucleus with the negation or complement of the original fixed element. So this was almost too symmetric. And then we noted that given a nucleus, we could form the collection of fixed points of it and whatever additional operation, necessarily Boolean or hiding one already to jump ahead, we could lift any operation from the signature to this nucleic quotient or the algebra of fixed points by simply prefixing the fixed point operator in front of it. And if one wants to be very careful and see the nucleic quotient embedded as a subalgebra into the original algebra, then we also have to make this identity embedding visible.
Mhm.
Yes, and that was a special case in the from which we started from Kripkean setting for a class model logic with classical over CPC with classical propositional base where you simply took, well, actually, instead of talking about forming conjunction or mid with the set, the subset of the frame to which we restrict, we prefer to look at taking a join with the complement of the set to which we restrict and then suitably leave the boxed operation. And then we see instances of this adjoint pair embedding. Well, actually, I should have lifted it a bit. Sorry. This part here. Oh, sorry. It would only work if I leave full screen mode. Let me do this quickly. So yeah, can I will need to ungroup this. No, I will not edit this picture now. Sorry. So if you
Don't do it.
well, I remember, especially Valentin Shechman with his word-based presentations, he's doing it all the time whenever he doesn't like
Mhm,
something in his
mhm.
slides. But no, with PowerPoint or Keynote, it's not a good idea. Okay, so if you leave this picture a little bit, if you go up with this thing, then you will see that this bottom here is matching this element of the original algebra complement of U, and the top here then matches the element um, of the original algebra. So we have an adjoint pair. The embedding, which is not a Boolean one because it does not preserve bottom in one direction, and then the homomorphism, well, Boolean homomorphism onto the collapse, which however does not necessarily preserve the box. Right. So let's return to the presentation mode, and then when moving in, well, what we were doing implicitly in the previous slides. So identifying now explicitly Boolean modal logic with equational theory of modal algebras or Boolean algebras of operators, we could give much more general definition of what it means to be subframe logic, namely being closed under nucleic quotients. And then the first observation was that Kripke subframe logics are subframes in this sense. So even if we start with the definition of our logic as given by a class of frames, which is closed under forming the subframe operation, then even if you pick some completely different algebra from this variety, which is not obtained as a dual of a Kripke frame, and choosing just some nucleus operation, which in Boolean setting means is obtained by this join with a fixed element, blah blah blah, we will know that the result of forming this nucleic quotient would fall into the original variety if the original class of frames was closed under forming subframes. Otherwise, not necessarily so. And for transitive modal logics, well, actually, this was something that was not stated well, at least on the slides. I said it, so it was in the oral part, but not in the written part of the presentation. Although this is, of course, a result that most people have seen or heard about before anyway. Not only the converse holds as well, this is what the slides were saying, but I should have written explicitly that they enjoy the final mole property, and this is most exciting or non-trivial result here. And then the Tbilisi group, Guram, Mamuka plus Silvio. Mamuka is not with us anymore, I guess, or is he?
No, not today.
No.
Maybe not yet.
Maybe not yet. Yes, maybe let's keep hope, because today I wanted him even more than last week to discuss some of the things that will show up later. Right. So they noted that this result still holds for so-called weak transitivity. So when you have the axioms that the axiom that P and box P implies box square, so box P. But already, if you look at the so-called two transitivity, box square P implies box to the third power, cubic box P, then subframe logics do not have to have final property, or even they don't have to be Kripke complete. If you yeah, this was not actually explicitly formulated in mentioning two transitivity by Frank Walter, but he gives the actual counterexample. It's famous fundamentum logic, which is quite often used in constructing incomplete logics, and its underlying frame satisfies this two transitivity axiom. Right. Well, and it's given by a general frame, of course, otherwise it would be Kripke complete, right? So syntactically, when we move to a broader setting of IPC, we noted that, of course, from one perspective, you can see this simply as a fragment of modal logic, the box fragment via the Gödel-McKinsey translation. In fact, rather than talking about absence of quasi-orders, we can talk about absence of partial orders, because absence do not distinguish points of clusters. And then cofinal or confinal properties sometimes have even simpler axioms in the intuitionistic original subframe logics. They may have even simpler axioms in the intuitionistic signature than in the Boolean modal signature. For example, the famous Whig law of excluded middle, or Whig-De Morgan law, as some topos theories would call it, not phi or not phi, is precisely this axiom of confluence that we saw in the first part. So even if you branch off, even if you have two incomparable successors, they still will have to have a common successor later on at some point. But of course, once again, the most general semantics is algebraic, and here is where Heyting algebras enter the picture. So this abounded lattices where meat has the right adjoint, which automatically implies distributivity law. And in this Heyting setting, it was again doing of Goran Bezhanishvili and Silvio Ghilardi. Actually, this was the main focus of the 2007 paper. They noted that also when you look at nuclei on Heyting algebras, and now the notion of nucleus is more abstract, it has just simply, so it's the real deal. So it has to, it is an operation of an algebra which simply has to satisfy these three axioms of being inflationary, being idempotent, and distributing over meets. A very strong form of transitive modality, as it were. They capture exactly this subframe construction on descriptive frames or priestly spaces or Sakya spaces where the definition of the subramization is natural generalization from cryptic rays, taking case also of which sets should be open, closed, or open. Right. So if we simply apply the definition of this nucleic lifting of for operations, even from the Heyting signature, of course, every Heyting operation on this on this nucleic quotient can be seen as obtained using this general definition here. But because of the fact that for some connectives or constants we have that for some connective or constants we have natural preservation or distribution law. So for example, nucleus always has to preserve top, nucleus always has to distribute over meets, and well, not sure if you can call it distribution over implication, because normal distribution over implication is much stronger law, which is not necessarily satisfied by all nuclei, but the law that nucleus of nucleus imply JA implies JB is the same thing as JA implies JB. So prefixing nucleus in front of implication, if both antecedent and the consequent are already prefixed by this nucleus operation, is spurious, is redundant, is unnecessary. So because of that, we don't even need to explicitly use this lifting idea. We can simply note that the collection of fixed points, this nucleic quotient, is already implicative subsemilatis of the original Heyting algebra, as it were. We can simply use the original join, original meet, meet, and implication and top. But it's not obvious for bottom already, as, okay, this should be stated. Yes, it's stated on the next slide, actually, I see that. So the subclass of nuclei preserving bottom is called dense. There are actually several other names. Peter Axel calls them strict, for example. I'm not sure what is the better name here. So already preservation of bottom is non-trivial, and with disjunction with join, that's of course a painful thing for a nucleus. This is where the interesting, where the most important bit of this actual nuclei of forming actual nucleic lifting of the original operation comes in. So you really have to say that the join in the nucleic quotient is actually obtained as nucleus applied to the join, even if both disjuncts are already themselves fixed points. But the good thing is that this idea where if your original algebra was already lattice complete, then this idea works also with infinitary joins as well. So you obtain not only you know that the nucleic quotient is lattice complete Heyting algebra whenever the original algebra was lattice complete, but the infinitary joins are also obtained following the same procedure. But of course, even though what you get is a Heyting algebra in its own right, even when you stick to Heyting signature and still worse so or less so if you work with additional connectives, you don't have any guarantee that all the equations, because of this funny business that is happening with even with bottom and even more so with join, you don't have any guarantee that all the equations that were valid in the original algebra will still remain valid in the quotient. And that's and being preserved by this operation from algebraic point of view is precisely what being subframe is all about. So yeah, this is something that I already mentioned, nuclei which are dense or in Axel's terminology strict, and then another of numerous results of Guram and Silvio was that this pre-existing notion of cofinal or confinal subframe logic corresponds to preservation by such dense nuclei. And if you, and as I mentioned last time, even if you broaden the definition of density or strictness a little bit, so instead of insisting on directly preserving bottom, you only insist that the negation, the complement of what nucleus does with bottom, or rather the nucleic closure, the results of application of nucleus to what to the complement of what the nucleus does with bottom is top. This is so-called locally dense nucleus if you satisfy this property. So even if you strengthen the condition to being preserved by this nucleus satisfying this weaker property, so you have to be respected by a Blow-Roeder class of nuclei, which is always harder. This would actually amount to the same thing from the point of view of at least varieties of Heyting algebras. We can pause for a second. It's not immediately obvious that this should be true also for the case where you have additional operators. That would require parsing Guram and Silvio's proof a bit. That this is also equivalent to being cofinal or confinal subframe logic. So with this introduction, we can recall then all those nice results that we said are true in the pure Heyting signature. So again, we have these fine results that subframe or nuclear logic have the finite frame property, which, as you remember in the model setting, require restriction to transitive or weakly transitive logics. We know that the logic over variety is nuclear if it's preserved by formulas. This is equations in this disjunction bottom free language, and we were shocked by this realization, which follows from quarter of a century old papers by Albert and co-authors, actually Dick de Jong and several other excellent people, that this is actually equivalent to being axiomatizable by syntactically completely different class of formulas, this nil formulas known as thing of implication to the left. And this is still equivalent to being axiomatized by formulas preserved by submodels of Kripke models and then subframes or Kripke frames. Yes, and the natural generalization of this to or strengthening, or well, not quite strengthening, it's simply a different result, is that you are locally dense nuclear or confinal subframe if you are axiomatized by mid implication bottom identities, so formulas not involving disjunction. So that's where we were. These are the things that were looking good last time. And then we started to see the first problems. We noted, for example, that there are types of nuclear quotients that do not preserve even this idea of being the dual of a Kripke frame. We will turn to this in a second, actually. And then, of course, question arose what happens when you have additional operations. So you have all the complications of the Heyting case, and now you put, for example, something like a modality on top of that. So you combine the fact that you don't. So we know for sure, for example, that even with box only, we are not able to establish anymore that all nuclear logics are Kripke subframes. And there are logics which are subframes, so preserved by this nuclear construction on algebras, but they are not necessarily Kripke complete, determined by any class of Kripke frames, much less closed under subframes. And of course, we also have additional degree of freedom whether or not we want to have a diamond in the signature. So these two connectives are not mutually definable in the intuitionistic setting anymore, just like existential and universal quantifier. And then you may have additional, for example, Fusser-Servi type of interaction axiom between those box and diamonds. And then what happens if you go broadly? Well, actually said most broadly in the sense of the three subsequent bullet points, right? So let's now consider a situation where you add a binary implication like connectives. And the first approach is to start with this Weiss minimal intuitionistic, basic intuitionistic conditional logic, ICK, where you only insist that this implication-like connective or arrow distributes over conjunction or mid in the second coordinate. Well, those type of logics requires either a neighborhood style semantics or a Chela-Spice semantics, where you assign a different accessibility relation to every element of the algebra, to every subset or every upset of your Kripke frame, or what we call generalized relative semantics, ternary semantics, where you have where you may have perhaps neighborhoods or upsets rather than states in one of the coordinates. Then you can still narrow this down. So you can take this ICK and insist that the arrow is moreover also transitive, admitting suitable generalization of necessitation. So whenever you have that phi in Heyting implies psi, you also have phi arrow psi being valid, always equal to top. And actually, I'm not sure if with Albert we stated this explicitly in the axiomatization of IA minus, but I think that we should actually insist that this thing is moreover anti-monotone in the first coordinate. Albert, if you're listening, this should be, so this anti-monotonicity rule, actually, which in the presence of congruence can be stated as an axiom. This also should be part of axiomatization of what we call IA minus, right?
Ah, yeah, probably.
Yeah, we were hand wavy about those kind of things, and I mean, of course, we want congruence at the very least. So you should be able to replace equivalence by equivalence on both coordinates. But I think that antimonicity, which does not follow in the absence of this axiom mentioned in the next line, DI, should be explicitly postulated for EA minus. And also because this set of axioms turns out to be so important, or this logic turns out to be so important in its own right, I'm beginning to wonder if we should not give it a more independent name. And so not implying that this is just IA missing something, but a worthy logic in its own right. Because, for example, as we already discussed last time with Daniel, I think this is already this IA minus is also the logic of type inhabitation of Haskell arrows. If you in the signature without join, well, then of course it doesn't matter whether you distinguish between those two systems or not. But it's really a system of its own in its own right, and also from the point of view of the next bullet, so preservativity of hiding arithmetic and its extension. This is always a safe set of axioms. And as I already wrote, just this weekend, I started to think if which one of those two systems, well, maybe first let me say what is the second system in question, full-blown IA, intuitionistic arrow, which was also called IP in Utrecht, some Utrecht Amsterdam papers by Rosalie, Dick de Jong, and the master student, Zhou. So it's the system IA minus. So you have distribution of over mid in the second coordinate, transitivity of arrow, admitting this generalized necessitation and being anti-monotone in the first coordinate. Actually, now you don't need this anti-monocytic explicitly because the new axioms axiom that we add, DI, is that mid conjunction of arrows with the same consequent is the same as arrow with join in the antecedent. Or rather, where if you have a join in the antecedent, you form a mid of arrow with the two disjuncts. So the right term for that would be, I guess, reverse preservation of joins, right? Or dual preservation of joins, actually. So this means that you're dealing with really something like an operator. If you're looking at all these papers on Boolean algebras with operators, sometimes they also they also assign or more generally lattices, distributive lattices and whatnot with operators. Sometimes they also assign order type on each coordinate, meaning whether you are supposed to preserve or dually preserve certain things. So you can already guess that this type of logic where you have that join well, actually, it's rather join being where it's rather mid being dually preserved. What is the right terminology? Anyway, so it means that you will allow a better kind of relational semantics, and that's indeed true. So IA is the logic of intuitionistic Kripke frames, where you interpret this additional arrow-like connective with binary rather than ternary accessibility relation. So unlike Rother-Meyer, but with the additional condition that this modal accessibility relation is actually closed under prefixing, but not necessarily postfixing with intuitionistic order. So whenever I can go up via intuitionistic order and then go somewhere to the side with the modal order, then it means I could already jump from the original state to the side with the modal order. And then you give the same definition of arrow or string implication as in classical Kripke frames. So you say that arrow is satisfied at a given state, even only if whenever a modal successor satisfies phi, it also has to satisfy psi. And this, because of this prefixing condition, this arrow will be closed under sorry, the notation of each arrow will be closed, upward close, which it will be an upset. Right. So this is why we thought this IA is actually naturally intuitionistic or constructive version of original C.I. Lewis, not C.S. Lewis from the Narnia stories, not David Lewis from Counterfactuals, but C.I. Lewis, Clarence Living Lewis, the original author on modal logic, strict implication, right? But now I started to have second thoughts over the weekend. I already mentioned this to Albert, but we didn't discuss this in detail. Whether this is actually fair to Lewis. So even if you want to, I mean, apart from the fact that he mistakenly in our review insisted that this strict implication should be actually definable in terms of box because his thinking was too Boolean, even though he was actually quite favorably inclined towards non-classical logics. But then if you go this way, then maybe you should say that not IA, but actually IA minus is the minimal logic of constructive strict implication. And that's because it's not obvious that weakest system that Lewis himself proposed, S1, actually satisfies this DI axiom. This is there is an old problem in the well, this is well known in the theory of those non-normal modal logics that you cannot give a really Kripkean semantics to S1. Even if you allow things like impossible words and non-normal words or distinguished words, you can only give Kripke style semantics starting from S2. Otherwise, you need some kind of neighborhood-like function, and that seems to be related to this failure or potential failure of to this failure of DI in S1. But this is taking us too far. So anyway, in our paper for the Brouwer issue of Indagnatones Mathematica, we were calling, I think we were focusing on IA, although we were not extremely precise on what we actually say is the minimal logic, Lewis, constructive Lewis or Lewis-Brouwer logic, as it were. But it might be that it should be officially renamed, and this logic with this undignified or an indistinguished name of II minus should be the real deal. And then, of course, Albert's interest came not from attempts to generalize Lewis, but it was coming from the study of meta-theory of Heyting arithmetic, as you can easily guess, and stuff that Albert was looking at for more than 30 years. So study of the notion of preservativity in Heyting arithmetic, which classically is just the contrapose of interpretability, but intuitionistically is a primitive notion in its own right. And actually, I will introduce this in detail. I will return to this in final slides. But I see that Albert turned on video, so maybe you wanted to comment or something.
Yeah, I just wanted to say that, so the special because for piano you don't have D, right? So it's a very special property of Heyting arithmetics and certain extensions. And so the proofs always use that you have closure under something like Q realizability or the De Jong translation. So you really need that your theory is closed under certain translations to show that you have D. So because if you look at ILM and then contrapose it, of course you do not have this property. And it also shows that sigma preservativity really, well, doesn't behave like converse interpretability in the Heyting case, right? It's quite different.
Yes.
So the convergence between pi1 conservativity and interpretability that you have in PA is completely gone. Anything looking remotely like it has disappeared over HA.
Yeah. we will return to this if time allows on 2 final slides, but it's good to make those points already. Sorry for those for whom it went a bit too quickly. So it was mostly a digression for people who like intuitionistic arithmetic, but this shows you why this started with discussions with, well, why discussions were one of 2 pillars on which this work is resting, and Albert's observation that something about preservativity, about preservation of the DE in the logic of preservativity may have something to do with a subprime phenomenon, but we will get to the details later. Yes, and then of course there are other theories whose, and of course when you look at Heyting arithmetic and this preservativity or probability or interpretability, you have various other laws that you know to be true. For example, various variants of the Loeb axiom, which has more than one way of stating it, especially now that you have binary rather than unary connective, and maybe more, right? Because we don't know exactly what is the logic of preservativity in Heyting arithmetic, just like we don't know what is even the logic of box of probability in Heyting arithmetic. Actually, one of several reasons why this notion of preservativity is interesting in the Heyting arithmetic in the HA case is that there are hopes that it would be actually easier to axiomatize this more powerful notion of preservativity, which includes probability as a special case. So it's again definability of box as top strongly implies. Right? So box phi in box can be defined in terms of strict implication. And this idea works in the special case of arithmetical preservativity versus probability too. And it seems that it's easier to get a grip on the valid set of on the set of valid axioms when you're working with this Heyting. When you're dealing with this binary preservativity connective. So even though we have neither axiomatization of preservativity nor axiomatization of probability, somehow the first notion seems more promising. And then, so this exhausts the setting of having just one single arrow-like connective. But then, of course, there are other signatures you may consider. If your arrow-like connective, which we may now write slightly differently, is actually happens to be adjoint to or to be a residual of a monoid operation, something which is associative and presumably also commutative, where sometimes commutativity is dropped and sometimes even associativity is dropped in some recent references, but the definition of original definition of BI includes those 2 conditions. Then you have you have here another example of an outstandingly important logic from computer science point of view, at least, which has Heyting reduct, which can be seen as generalized modal or intuitionistic modal logic in a broader sense. If you look at, for example, how the Dutch book Blackburn, Verema, and de Rijk define modal logics, this would be an example of a modal intuitionistic modal signature if they were ever considering intuitionistic modal logics. So all those logics allow different types of semantics, Chelas-Weiss, generalized Rother-Meyer, generalized Weltman, I didn't speak about this at all, or in the case of BI, various variants of partial monoid semantics, which can be seen as a special case of generalized Rother-Meyer semantics, also topologically generalized. And then you could, of course, try to define from the scratch what being a subframe logic in all those contexts is. Or you can simply stick to this nuclear idea and try to take it on the other side via duality. Right. So, and then the question is, of course, to begin with, what are those subframe logics? What properties do they have? what kind of results we can prove about them. So we have to start building some kind of general theory, also taking into account this problem that sometimes you won't even have that these nuclear collapses will preserve being a dual of a frame. And the start, and here is where this, well, so after 45 minutes almost, I'm beginning to give a proper talk again. So yeah, so here I want to introduce another notion from Walter's toolbox. He was speaking of describable operations. Actually, I started to give this definition last time in just before 6 p.m. So if you start with a notion of a set valued operation on a given class of algebras, so assigning to a given algebra a set, which in most cases would be a finite set in what we are going to consider further. We can always extend it to subclasses by taking set theoretic union. And then if we want our operation to behave at least a bit like forming those subframe or nucleic collapse, you will probably you will need it to satisfy some additional laws, such as being delimited. So, well, half idempotent would be another name. So, doing this operation twice on a class of algebras should not make it any bigger than doing it once. And you may, but this will not actually be a sensible requirement for at least some of the operations we will be talking about now. It makes sense for the original subframe or cofinite subframe construction. Insist that it is inflationary. So the closure of a given class of algebras contains this class of algebras. And of course, if you look at forming of nucleic quotients of a given class of Heyting algebra expansions, these two laws, these two additional properties are satisfied. But then in the Boolean setting, we do have another property which will be more problematic in the Heyting case. What is it? Well, let's assume that we have a formula or an equation which holds across all these nucleic quotients or in all subframes of your original frame. Now the question is if we really need to check its validity by checking all of those quotients, all of those subframes, or is it enough to look at the original algebra and tweak the starting formula somehow? So introduce some kind of transformation, translation, nucleic translation, which you can call already jumping ahead a bit. We can suggest that it's going to be nucleic Gödel-Gensen or generalized negative translation. And indeed, this works in a very simple way in the Boolean setting. So you first of all have to fix the variable which is fresh for this original formula, and then do this closed translation in using the join with this fresh variable and prefixing it in front of every subformula. In fact, it's enough to, in the Boolean setting, if your primitive connectives are just negation and conjunction, to do it in front of atoms and in front of negation. So the bracketing here is like this. And of course, form the suitable relativization also for the box operation. If you want to reflect syntactically what was happening, you remember we had this adjoint part of mappings, this homomorphism, Boolean homomorphism, not necessarily box homomorphism, forming the nucleic quotients, and the reverse mapping, which was not necessarily even a Boolean embedding. and then observation that goes back to Kracht and Volter is who formulated in a slightly different way, because they would chose the diamond perspective. So they didn't look at the complement of the original set, but they were restricting things down and forming the conjunction with P, which is blurring this nucleic perspective. So then you can show that indeed it is the case that a given formula holds in the class of all nucleic quotients and in the class of all subframes, even only if the formula obtained by this the transformation of this formula via this translation holds in the original algebra. And whenever for your set valued operation you have such a transformation on formulas or equations, we will call it satisfying this property. We will call it this C weakly describable operation with this subscript C or subscript J being the describing translation. Right, so hopefully this is clear. And then we see yet another problem in the heightening signature, which I was already alluding to the last time. So the lattice of nuclei, as we already agreed on heightening algebra, is quite complex. And then let us look again at all these examples of nuclei in the heightening setting that we walked through last time. Maybe now let me just make more explicit that the two papers, classic papers from which I took them, is on the one hand shift-left logic by Fuhrman and Scott, and on the other hand McNabb's paper on modal operators or heightening algebras. So we have, I was already using this terminology quite a bit. So we have the closed quotient join with a fixed atom or a fixed element of the algebra. We have the open quotient, so forming the implication with a fixed atom or fixed element of the algebra as the antecedent. We have the Boolean quotient when you allow this fixed atom or fixed element of the algebra to play the role of bottom. And the reason why it's called this way is that this is the so to say richest Boolean algebra that you can obtain by taking your A as the bottom element. But so there are things that go that get more. This is very important type of nucleus, but it is already behaving in a more problematic way than the closed quotient and the open quotient. So first of all, recall this notion of being dense or strict, preserving bottom. You could easily see that this closed quotient will include strict nucleus as a special case where you pick this A here to be bottom. Similarly, the open quotient will be strict dense or bottom preserving if you pick this A to be top. And moreover, in both of those bullet points, this density will actually mean that the nucleus in question includes identity as a special case. So jumping ahead a bit, if you talk about the class of corresponding nucleic collapses, it will be extensive, or it will be inflationary. The original algebra will always will always belong to the class of all its closed quotients and to the class of its open quotients. But it's not necessarily the case if the original algebra was not Boolean with the Boolean quotient. Even though actually when picking this A to be bottom, which is a very important nucleus in its own right, it will be dense, right? So double negation of phi preserves bottom, is strict. Double negation of bottom is still bottom again. But of course, if your algebra was originally heightening, it will not be. and not just a Boolean algebra in disguise, it will not necessarily be, it will not be isomorphism, it will not be identity original algebra, the collapsed algebra will be a Boolean one, right? So let us, in fact, denote, because that was another inspiration apart from the work with Albert, let us even pick this special case where A is taken to be bottom as the double negation quotient, which can be written as B bottom or W bottom. And these are the three most important type of nuclei that, that there are. In a special sense, even all other nuclei can be seen as obtained from those three guys if you allow things like infinitary conjunction, for example, over all elements of the algebra. But of course, that's not a trick that you can do in purely equational language of Heyting algebra expansions. So there are other types of nuclei or nuclei quotients that one can be interested in. This Sheaves and Logic paper gives a special example, the forcing quotient, which can be seen as forming meets of closed and open quotients. So you have now two parameters instead of one. You form join with the first of them, implication with the second of them as the antecedent, and you form meet of whatever you have, which will again be dense and identity for a equal to bottom. And then there are various types of mixed quotient. I didn't want to use the definite article D, the mixed quotient, but the special mixed quotient that they were considering was obtained by taking meet of the Boolean quotient and the open one. It can be actually written in much more compact way, so almost looking like the Boolean quotient when you replace this fixed item by the argument itself in the consequent. I remember that Mamuka was telling me that there are still new types of nuclear or quotients being discovered. In particular, Martin Escardo apparently boasted to him a few years ago in Prague that there is a new type of quotient that seems to be important in its own right, which is slightly orthogonal to this list, but I never heard back, and Mamuka is not here, so I can press him. What are these other examples?
May I ask a question suggested by your slide? So you have here certain operations on this nuclei, and presumably, if you
sorry,
consider
can I correct? We have here various term-defined operations which give nuclei.
Yes, but the question is the following. So consider the set of all nuclei on a given algebra.
Mm-hmm.
Does it bear the structure of, let's say, an algebra in its own right?
Yeah, so this is something that is very extensively studied in point-free topology. So when you start with complete Heyting algebras, so-called local or a frame, this is very confusing, but they use this term frame here. A lot of effort for a number of reasons that Mamuka, if he was here, sadly, he's not with us right now, would be able to tell you quite a bit. So it's like it's a bit like point-free generalization of this investigation by Simons that we were also discussing last week. There is a lot of effort that has gone into the study of the frame of nuclei on a given frame. So they form a complete Heyting nuclei form a complete on a given complete Heyting algebra, form a complete Heyting algebra in its own right, which is much bigger. And while it's easy to describe meets in this algebra pointwise, description of joins is already much more painful. And actually, one of well-known results of Dito Pataraya on describing fixed points constructively got a lot of attention there, because there were like 4 or 5 different ways of describing how joins in this complete Heyting algebra of nuclei on a given complete Heyting algebra looks like. And perhaps the most promising one from the point-free point of view uses this Pataraya fixed point theorem. So there is a lot of interesting constructive mathematics, which also generalizes some sophisticated topological reasoning here. That's a really
and if the algebra is not necessarily complete, so in the incomplete case, did people study such structures as well?
Less so, because then so I remember reading some remarks and maybe some scattered references on this. I'm not Mamuka to really answer this question competently. Maybe even Daniel can even answer better than myself. But I remember, if I remember correctly, it doesn't even have to be a Heyting algebra, if I'm not mistaken. I will look for some basic references, or at least places where observation. Right, even this McNabb paper that I was mentioning, in this 1981 paper, yes, about model operators and Heyting algebra. This is what makes his paper different, actually, because as you see in this Fuhrman and Scott paper, they were dealing with topospheretic motivation, so they were or point-free topological motivation. So of course the Heyting algebras were always complete, but McNabb did not assume that he has infinitary conjunction and disjunction. So anything that starts from McNabb is a possible reference here. But in general, things are messy.
But lattices probably we do have. So we do have.
I'm not even sure about this.
Lower and upper bound.
So you may need to embed to move from nuclei to pre-nuclei. So when you are inflationary, where you assume preservation of meats, but you don't insist of being idempotent. Otherwise, I'm not even sure how to compute join. You see, even binary join. But again, I'm slightly outside of my main area of expertise here.
No, that's enough information for me. Yes, okay.
But I will follow this up, and if anybody is interested, they can be also put on CC or whatever, or added to the slides in the light of this discussion. Yes, but this is actually very important points indeed. So things are Heyting, and even much better than Heyting, complete Heyting again, if you start with a complete Heyting algebra. And indeed, it's a very natural idea to study this. Well, natural if you have like left good mathematical sense to look at the complicated structure of all possible nuclei or on a given local. Right. So, but before we start to look at all possible nuclei, I mean, each of those special instances of what following Axel we could call lax modalities, or actually to be more specific, to insist that we really want them to be definable in the modal, or even in the Heyting language maybe itself. So for each of those instances of definable lax modalities, we can consider the corresponding class of nucleic quotients. So we obtain them in a obvious way. I didn't want to put a detailed syntactic definition on the slides, because somehow whenever I write it up, it gets a bit hard to read, a bit too heavy on notation for such a simple idea. But the basic idea is you had this A everywhere, this fixed atom, or in the case of some of those quotients, like the mixed quotient or the forcing quotients, 2 parameters B used in this definition. And then when you look at, when you start with a given algebra, and when you vary the valuation of this atom across all elements of the algebra, in each instance you are obtaining a nucleus. separate nucleus, right? So you can consider in the closed case joins with a fixed element of the algebra. In the case of open nucleus, you can consider implies from an element of the algebra, and so on and so on and so on. In the case of double negation, there is no parameter to evaluate, right? It's defined in the constant language. So there is just one single quotient, which is this double negation quotient or collapse. So each of them will be, well, I say clearly, actually it's maybe that's so immediate to see, but each of them will be weakly describable in this sense, generalizing this simple Boolean idea that we have seen from Kracht and Volter. So you can use this generalized Gödel-Gensen translation when you apply your nucleus, where these parameters A and B are taken to be fresh variables to atoms to join and to modal operators or whatever additional operators you have. And then an equation, a formula will be valid across the class of all quotients, even only if it's Gödel-Gensen translation with fresh A and fresh B will be valid in the original algebra. But how to describe the class of all nucleic quotients, right? There is no obvious syntactic structure to it anymore. I mentioned that in a sense, all of them can be seen, for example, as obtained if you are lattice complete, if you have infinite joins and meets, as taking suitable infinite joins of these Boolean quotients, where you range over all elements of the original algebra. But clearly, this is not what we would accept as a good, that would falls under this notion of describability when you're dealing with purely algebraic equational language. So Nick and Guram and Nick's former student Yulia Ilin in the recent GLC paper, which is, by the way, excellent reading, subpremization and stabilization in inductionistic logic, kind of resorted to a trick. So they noted that each intermediate logic can be axiomatized by canonical formulas of Zaharyashchev, and on those on this subclass, providing corresponding Gödel-Gensen or nucleic translation is near trivial. So there are these closed domains for those of you who are familiar with how those canonical formulas work, and you just remove those distinguished domains which have to do with preservation of joints, if I remember correctly, and that's it. But then, of course, you need to rewrite your axiomatization into this canonical form, and it's not clear to me at all if there is a discursive translation of low complexity for arbitrary formulas. And then things get much more problematic if our signature includes additional operations, such as this arrow-like connective, such as boxes, diamonds, fusions, and whatever. So then it makes sense, even if we cannot do it for arbitrary nuclei, it makes sense to form to try to provide a theory of describable classes of nuclear quotients. So see what happens to logics which are preserved by open nuclei. See what happens to logics which are preserved by closed nuclei, Boolean nuclei, or otherwise. And in fact, this is not purely intellectual exercise just to see what is easier. As I said, the two motivating examples for me arose completely independently. One in my study of negative translation for inductionistic modal logics, which has to do, of course, with this double negation quotient, and the other one being Albert's interest in preservativity logics. So some of basic facts that one can easily prove, generalizing essentially what Frank Volter is already doing in his dissertation, is that well, first of all, if you define, you remember that we have this notion of being stabilizing as being half idempotent, so doing operation of nucleic collapse or whatever it was twice was not making this algebra any bigger. Well, if your operation is weakly describable, this means that whenever you look at the validity of the formula in the class of all the nucleic quotients, then this nucleic translation will be valid across the class of nucleic quotients as well. And being subsuming, so or inflationary, so the fact that the original algebra belongs to the class of all these nucleic collapses means in particular that whenever phi was valid across the class of nucleic collapses, of course, it also has to be valid in the original algebra. So if you forget now, so we are already moving closer and closer to syntax, and now if you forget completely about those algebras and look what is happening on purely syntactic level of the logic itself, then this being stabilizing means that what you obtain by forming this nucleic Gödel-Densen translation of for your describable nucleic operation twice is already contained in the logic axiomatized by the sorry, we are not talking yet about set of axioms. This is actually non-trivial that you can restrict your attention to the set of axioms. So that for any formula, we will have that doing this negative translation twice does not yield anything new that you couldn't obtain by doing this nucleic translation once. Similarly, being subsuming means that you could not produce, you could reproduce the formula from its nucleic translation using the deductive closure. So having this condition on the semantic level being delimited, half idempotent, and weakly describable, so having this suitable C implies being stabilizing in this sense, and being extensive, so having this inflationary condition on the semantic level implies being subsuming. And when we have all those conditions, we can say that our weakly describable operation is really describable, fully describable, or Voltairian, because that was the definition that was used by Frank Volter. Of course, then we note that subramization or nucleization operation on Boolean algebra expansions is fully describable, putting together those several observations that we have. And then, because as I said, I want to take care of such things like double negation translation, I'm not really fine with insisting that on this Voltairian notion of describability. In particular, I'm willing to give up this condition of being inflationary or extensive, as I already explained before. So the meta theory has to be developed using some slightly finer distinction than Frank Volter had in his dissertation. And we can also say what it means for a logic to be complete with respect to a class of given nucleic quotients or a subframe, C subframe for a given set valued operation, or C complete. This is the notion that Frank Volter is using in his dissertation, although it's maybe not the best one here. So this means simply that for a given subvariety, the class of the quotients belongs to the subvariety itself. And if you are extensive, of course, you can reformulate it with, like Frank Volter is doing in his dissertation, with equality instead of inclusion. So the first general meta theorem that one can prove is that whenever you have such a weakly describable operation, like forming those open quotient, closed quotients, or Boolean quotients, the C completeness or C subframeness, or however we want to call it, is equivalent to admissibility of the rule from phi infer its generalized Gödel-Gensen translation. And moreover, and that's actually important observation, it's enough to look at the axiom. So you have a logic given by a finite set of axioms, and you have such a describable operation, and you want to see if this logic is cool with this, is safe with respect to this corresponding class of nucleic collapses. And then you can use decision procedure for your original logic, if you have one. And look if after forming this generalized translation of given by this describable operation on the axioms, actually always produces in this finitely many cases produces something that belongs to to your logic itself. So the first time when I realized this was when I was looking again at the behavior of the double negation in the modal case. I realized that not all modal logics are double negation complete or double negation subframe. That there are instances where double negation translation of something which belonged to original intuitionistic modal logic, even in the language with box only, does not belong to the logic itself anymore. And as you can maybe imagine, the problematic axioms are those which are not likely to perform well with respect to subframes, such as this density axiom, that not the intuitionistic density, but the modal density, that box phi implies box phi. Several other ones like generalizations of transitivity, for example. But this works in much bigger, broader setting. So another trick that Nick, Guram, and Julia were doing for arbitrary nuclei, it should be not nuclei, sorry, that's a horrible typo. We're doing even in the pure Heyting setting. Because you have problems with this very notion of describability, what they were doing was to add additional modality into the language, a lax modality, as it were. And then they were doing this generalized Gödel-Gensen translation with respect to this expanded language. But then it means that if you have, even if you have a decision procedure for the original logic, it doesn't necessarily need to yield a decision procedure for the logic expanded with this additional modality, which is supposed to satisfy some additional laws. And then you could use also other ideas such as this Volter-Zaharyashchev generalization of the Gödel-McKinsey translation into classical bimodal logics. For those signatures and for those logics where something like this is a variable for intuitionistic modal logic with box only. Or for the IA logic, but this is something that we're still working on with collaborators in Canberra. Okay, this is going a bit too far ahead. So another meta theorem that one can show for arbitrary weakly describable operation, not even satisfying any of those additional properties that we mentioned, is that those C complete logics or C subframe logics form a complete join subsimilatis of the lattice of all logics. So existing joins are preserved by infinitary, meet infinitary. Sometimes I'm saying the opposite thing. Complete meet subsimilatis of the lattice of all logic. So existing infinite meets are preserved, but not necessarily infinite joins. So that's something that always holds. And then if you have this additional properties, the stabilization, which we call boil down to double translation of the of all axioms belonging to the logic obtained by single translation, non-iterated translation of all axioms, then you already know how to axiomatize, for example, the least C subframe or C complete logic containing your gamma. simply by taking the original set of axioms and putting it together with the generalized Gergensen translations. And if you have this additional property of being inflationary or extensive, so if you are really doing in a Voltairian cycling, you can also obtain the least C subframe logics contained in the logic in question. The greatest C-complete logic contained in the logic in question this way. It's the second bullet point. And the first bullet point is that moreover, the description of the least C-complete logic over your logic can be simplified. So instead of taking both the original axioms and the translated axioms, it's just enough, of course, to take translated axioms only. And then if you have all those properties like Voltaire originally wanted, it's really a complete complete sublattice, or no, not subcomplete lattice, that sounds stupid, but both infinitary joints and infinitary meets are preserved. So these are general facts, and now, well, I'm running out of time anyway, and everybody's quite tired. I think maybe I spent too much time on recalling and putting together what we knew from the last week. But the really difficult, something which turned, well, maybe not really difficult, but surprisingly difficult question, something that got me blocked for quite a while, actually. This is why I didn't submit in March when I was in Utrecht with Albert, apart from all this Corona thing exploding, borders being closed, me having to evacuate and whatnot, was that I realized that I don't have a good criterion of what it means to be stabilizing. So at least having this property that forming this nucleic quotient twice is not giving you anything more than forming, iterating it is not giving you anything more than doing it just once. Yeah, I wanted actually to walk through it, but again, after 80 minutes, probably it's a bit too much. So let me just say that there are those two laws that need to be satisfied whenever I rename the axioms. I need to find a substitution which satisfies some additional properties, and then for suitably well-behaved or well-defined nuclei. For example, those that are defined by Heyting formula, which is not using any bottom and disjunction. This criterion can be dramatically simplified. But even for some of formulas which are involving disjunction, such as the closed quotient, we have pretty nice criteria. So, well, maybe let's see. Again, we have no time to walk through this. How you will apply those criteria to show that actually the open nucleus, the closed nucleus, and the Boolean nucleus are actually stabilizing. So they satisfy this property that it's enough to do everything just once. I still don't know what is happening in the case of the forcing quotient and the mixed quotient. So for the basic ones, I know that they are at least stabilizing, but the criteria as there are the corollaries that I obtain, well, maybe they are sufficiently strong to prove stabilization, assuming that it holds at all for the Boolean, for the mixed quotient and the forcing quotient. But I will need to find a suitable substitution, which I wasn't able to find yet. And the one which is the most obvious was one doesn't work. It does seem to have with the composability of the nucleus or composability of a monad with itself. So this way I was hoping again that Mamuka will be here to discuss it with him, but maybe let's not bore people with this. If anyone who wants to can discuss this with me later. It is much easier to say, though, what it means to be subsuming or extensive or inflationary. So it is enough simply that there is a valuation that turns your nucleus into identity. And we have seen this already, right? So we have seen that it works for open, closed, forcing, and mixed quotient. The only problematic ones among the examples that we have seen are double negation and Boolean quotients. And Volter then kept noting additional nice properties of Boolean of the nucleization on Boolean algebras, such as that the corresponding translation is computable and decidable. This we have for all describable operations. A finite algebra is on a finite set of finite ones. This we have for all describable nuclei. But already this property, as we pointed out last time, that if you have something which is a dual of a Kripke frame, so are all algebras so are all its nucleic quotients. That doesn't need to be true anymore. So even if you restrict attention to the pure Heyting signature, that we had this problem with Boolean quotients, as discussed in detail, and now things can get even worse when we are living in the presence of additional operators. Sorry, actually, are people following? Because two pictures seem to be frozen, both of Levin's. No, okay, yeah, everything is.
No,
I'm still online. Good.
yes, everything.
So. Okay, so maybe it was just Zoom reacting slowly on my side. Right, but now things can go even more wrong. So even for those nuclei which were unproblematic in a pure Heyting signature, such as the open nucleus, the one which was obtained by taking implication to something, some of these axioms, such as this DE that we discussed in the context of constructive string implication, they may not preserve them. So even if you had a dual algebra of a Kripke frame with this additional binary operation, things can go wrong, and you are not a dual algebra of a Kripke frame, of an intuitionistic Kripke frame anymore. So yeah, now I should be wrapping this up. So the concrete examples that I had were those two that I kept mentioning throughout this talk all the time. As I said, one of them with Miriam, and Miriam was already mentioned in the title slide, and another co-author was another one of my students. We studied this notion of double negation completeness or double negation subframe, which had to do with satisfaction of one of the Simpson criteria, or what it means to be actually a real, well-behaved intuitionistic modal logic. So is it the case that you are a intuitionistic counterpart of some classical modal logic? But then what it means to be intuitionistic counterpart of some classical modal logic? One obvious definition would be that there is a classical modal. So if you start from yourself, even from the intuitionistic modal logic that you're interested in, and add excluded middle or double negation or whatever, then would that be the case that for every formula, the formula will belong to this classical logic in question, even only if its double negation translation will belong to the intuitionistic modal logic in question? And as I said, it turns out that this is not necessarily the case for non-necessary subframe-like axioms, such as density or suitable generalizations of transitivity. And that was an example of a non-extensive operation, non-inflationary one, which was nevertheless very natural. And this is why I realized that I need to study Voltaire's ideas even in broader generality. On the other hand, there were also theorems there that easily apply to this much broader setting, such as, for example, isolating a class of what we called enveloped implications, which was always behaving well with respect to this double negation translation, which is with suitable Kerr generalizable to this much broader setting to preservation by a given describable nucleus or definable Lax modality. And at the same time, things that we didn't need to worry about in this original double negation paper can break down on much more basic level if you allow non-box-like modalities, because in our paper, we're only looking at unary boxes. And even if you have diamond preserving joins, and even if you restrict your attention to double negation quotient, here is a simple example which shows that taking this operation of forming double negation quotient and applying directly this definition of nucleic lifting for diamond may break things down completely. So if you just insist that the diamond preserves joins, and then you take this 5-element Heyting algebra, and then you take simple diamond, which is taking everything to bottom apart from the top itself, right? This thing is clearly preserving joins. Then when you look at what happens at the double negation of the translation of this thing, so the largest Boolean algebra containing bottom, these three guys will survive, this one will not, so you will have the 4-element diamond. And then the lifted, well, diamond, it's trapezoid or square or whatever, let's not use the same word diamond here. And then the diamond on this 4-element algebra will not preserve joins anymore if you just use the lifted, the nucleic definition of diamond, so double negation of diamond in the original algebra. Right. So this can go wrong. And then if you look at more complicated signatures, such as that of bunch implications, then things can go wrong in even more dramatic way. So the situation is almost an opposite of what you would expect looking at intuitionistic versus classical model logic. The intuitionistic logic of bunch implications is decidable, whereas its Boolean variant, where you add just excluded middle to this minimal logic BI, is not. So this means that there cannot be any recursive translation at all, which is embedding the Boolean part into intuitionistic one, because then you could use the existing decision procedure for the logic of bunch implications, intuitionistic logic of bunch implications, and decide the Boolean variant. So here, this whole business of double negation translation fails for much deeper reasons in much more dramatic way. And then still going further and further out of time and patience of the audience. But fortunately, we discussed this already quite a bit. The other case study that we had was with extension stability for logics of arithmetical interpretations. So when you have this constructive street implication connective, binary arrow-like connective, and if you fix your arithmetical Fiore and a set of sentences, normally these are just sigma 1 sentences, then you say that under your fixed interpretation, we have that A strictly implies, or Lewis implies B, if for every, let's say, sigma 1 sentence, S, whenever the Fiore in question contains or entails that S implies A, you also have that S implies B. But there are, of course, many other interpretations of such binary connective which you can consider. And just the most general condition that we need, which we can call being an elegant interpretation, is that for any recursively axiomatizable arithmetical Fiore U and any triple of arithmetical sentences, we have that B strictly implies C, even only if A implies B, strictly implies A implies C. So if we have this condition, which we have for this preservativity, and for most natural interpretations of implication-like connectives in the arithmetical language, we can ask whether this is in general a case that if you extend your Fiore with finite set of axioms, or to be more specific, even with a single additional axiom, because remember, you have two different parameters now, right? You have the interpretation of the connective itself, but you also have the syntactical formula in the language of Heyting arithmetic, which you use to translate, but you also vary the Fiori on the left-hand side of the turnstile arrow. So is this monotone? So when you move from a Fiori to its extension with a finite set of axioms, will you always obtain more Fyodor Pahomov? You will always obtain more axioms which were than you had when you started just with the simpler axiomatization. So in other words, master principle valid in the base theory hold its in all its finite extensions. And actually, the very logic of preservativity turns out to be problematic here. So Markov principle can be axiomatized because Markov principle can be axiomatized by a single sentence. And this already shows that things break down. So we can say that our arithmetical logic is extension stable if this question mark condition holds for an elegant interpretation of. And as it turns out, the study of extension stability is the study of preservation by those open nuclei which are from atom implies. So from purely syntactic or modal point of view, this is what this is, or algebraic point of view, this is what this arithmetical notion boils down to. It corresponds to being a special type of a subframe logic. But the problem is then, of course, we are dealing not with AI, but EA minus as a basic theory. IA minus is always fine, but not necessarily this DE axiom that we discussed extensively, which means that you should not use a semantics, which like this binary-Kripke semantics requires DI. As I said, you probably require some, well, there are those Cella style semantics or generalized Roger-Meyer, which are a bit painful to work with. And if you want to make things nicer, you want to use a suitably generalized notion of Veltman semantics. And this is final slide after all this marathon. So further examples that are not even fully developed is to look at what happens by if you actually use additional signature. If you have nuclei definable, for example, in the language of the logic of bunch implications, such as T fusion P, top fusion P, which yields the collection of intuitionistic affine assertions, something quite important in computer science and in separation logic. That's something that we're discussing Georg Struve. And then another important use of nuclei is in algebraic CAD elimination and non-style completeness proofs for substructural logics. But then they are using completely different, well, not completely. They're using different or stronger notion of nucleus where you have to preserve fusion rather than lattice mid. So here, if you move from intuitionistic to substructural setting, there are different choices that you can make, and theory would require adjustments. Okay, thank you for your immense patience. It was really way too long. So if there are still people who are not exhausted and have questions, I'm willing to take them.
Yeah, sure. Thank you very much. That was a very interesting presentation and a very good survey also. Okay, who wants to ask a question? If not, then I will ask my question. So the question is not, let's say, kind of general, very general question. So you kind of the moral, what is the moral of your talk and study? So nuclei are somehow useful in explaining several things that we study. And the first point that was rather clearly made was that they help to understand this subframe logics and conditions closure under this subframe closure operations, etc., etc. So this whole general approach to subframe logic, which allows them to transfer them to further settings, so to say, this whole. So what was that the main point, or was there anything
No,
else?
the main point is that if one takes even this basic theory developed by Volter, and even working on a purely algebraic level, then the basic meta theories such as obtaining a criteria, even algorithmic criteria, assuming that you're working with logics which have decision procedures, will apply to several notions of interest in its own right. So independently studied, such as this double negation completeness or soundness of the negative translation in the inductionistic monologic setting, or this logic of preservativity in the Heyting setting. So you know, for example,
so this Volter's ideas that you mentioned are essentially this criteria of definability of this nuclear. So what happens if your nucleus is definable, and then there are certain benefits you can sort of
yeah, so there were those general theorems. Maybe let me move back. Sorry, let me move back a few slides. So I gave where was that? Not here, not here. Right. So there are those general Verger meta theorems when your set of how to axiomatize, for example, the least double negation closed, or the least extension stable logic contained in your
okay. And so these theorems, for example, they also apply to the preservativity case, or I missed the point. There was this niceness property. Is it the same niceness condition that
niceness was additional? So there are additional meta theorems involving this niceness notion. So whatever was, whichever theorem in Volter's dissertation was using actually just the two first bullet points from this niceness definition, and not the third one, which is much more problematic. So being well behaved with respect to Kripke semantics, but just being algorithmic, or being having a decidable or recursive translation, and finitely many instances out of a finite algebra. All those results will apply as well. But I didn't even list or mention those theorems, sorry. So you are indeed right that there should have been more structure here. But even if you forget about this additional niceness conditions, even if you look at just those basic theorems listed here, we can indeed apply them already to, let's say, logic of preservativity, because we know that it is actually that the corresponding weakly describable operation is actually stabilizing, and in fact it is fully Volterian. So we know, for example, how you axiomatize the least extension stable logic over a given set of axioms. We know how to axiomatize the greatest extension stable logic contained in a given logic, given in a set of axioms. We know also those additional facts, such as this preservation of complete joints, complete meets by the lattice of extension stable logics, for example. And the same, well, we don't have this for the, we don't have the second theorem for the double negation, because this operation is not Volterian, but we have the first one. So these are the things that we obtain relatively easily. And now if you want to put semantics and duality in play, then this should be a second, or as it were, or the third part of this talk or of this work, where we actually start to study more systematically those dual types of semantics or representation for specific classes of algebras that I was looking at, and looking at what this operation of nucleization actually amounts to on the dual side. But I'm not sure how exciting it is to do things purely on algebraic side. But this type of results, such as the one that you see on this slide, these things you can do already in purely algebraic setting.
Okay. By the way, the term Voltairean is very nice, because
yeah.
you know why.
Yeah, I know.
So in Russian 19th century literature,
Mm-hmm.
you know, there was, of course, the term Voltairean in a different sense of,
Yeah,
of
well,
the
that
word.
probably the last truly Voltairean novel in Russian literature was Moskva Pietushki, right? The Enlightenment novel about traveling from one place to another. This is taking us a bit too far from the original setup. But yes, Frank Walter has the privilege of having very nice surname. I'm not sure if he's originally from Berlin, because Berlin had particularly many Huguenots, so people of French origin. This is why it also has a reputation of being a bit more witty and having slightly different culinary tastes than even surrounding cities in the same area of Germany. And so it might very
Do you
well be
think
that
it
Frank himself
could come from the same root, so to say, the two names?
I wouldn't. I do regret that Frank Walter is not with us today. I mentioned this talk and he was interested, but he said he's sitting on interviewing panel the whole day. If he was, I would press him about the depth of his genealogical tree and what he knows about, I don't know, 18th century. Because there are stories in the literature of, I don't know, German soldiers who surprised Napoleon invading army by insulting them in the purest French language, right? These were the Huguenots defending themselves against French invaders. So maybe Frank Walter's family was one of them.
Okay. Okay. So anyone else? I have a very small question, maybe even for Albert. So this Friedman translation, obviously in the so it begins like this closed nucleus, right? Like P or phi, so to say. But then it does not fully has all the conditions of on operation defined by a nucleus, right? So it has some similarity with all this.
It's only defined on the axioms, or I'm sorry, on the atoms, right?
Indeed.
That's the difference. Yeah, wait a moment. And so we, at least in Kripke models, I know what it means. It means that you can you explode certain you explode certain classes of nodes, right? So you said it really means that omitting in a Kripke model, it means omitting the nodes that force phi, if you Friedman translate with respect to phi. Yeah, so I don't quite know what the relation with nuclei is. It should, but you're certainly right that it seems to be related.
That's interesting. So the definition of the Friedman translation says
I think there's probably a whole cloud of Friedman translations, but the simplest is precisely that you take the atoms and add or phi. And so, for example, you can use the Friedman translation to prove closure under the independence of premise rule, to for example, right? HA.
Yeah.
So that's the kind of thing you can do with it, or closure under the under Markov's rule.
Markov rule, yes. Yeah. Very useful. Very useful translation.
That uses a special property, of course, of the sigma formulas, but yes. So it's an extremely useful thing. But so the whole thing is you only put the disjunct or phi at the level
of atoms.
But you do not iterate it. But I think they used, so I think there are other Friedman, so I think the kind of variations that we saw for the nuclei probably also exist for in the Friedman case, but I never studied these further things.
That would be very interesting for me because that would make picture nicely symmetric. So on the one hand, we know that open preservation by open nuclei is just another way of saying that you are extension stable. So if there is a way of putting Friedman translation, which sounds very much like closed nucleus to me, and we have both open nuclei and closed nuclei in the meta-pure of arithmetic.
Yeah, so
with double negation, we also don't have to put it everywhere, right? We put it at crucial points.
Precisely. But you can put it everywhere.
But you can put it everywhere, and then it will be
but that's
proper translation in that sense.
But that's not true for in the Friedman case.
In Friedman, we will spoil if we put it everywhere, right? We will.
Oh, is this already known? So are there already good examples in the literature that things break down if you put it everywhere?
Okay, wait a moment. So we Friedman translate or yeah, I guess so, right? Because if you put it everywhere, it will be on the outside. So if it's, for example, or the consistency statement, so by the disjunction property, then to prove anything. So take HA, right? And take the generalized Friedman translation where you put the disjunction everywhere. And now take, for example, con HA. So, but then for anything that okay, wait a moment. No, sorry, it's not a good example. I'm sure that it. Okay, wait.
And the other problem is, of course, that you're making here a disjunction not with atom, but with some arbitrary sentence, right? So
yeah,
yeah, but that's all right. We are in a kind of even uses are in predicate logic even, so it's but so that P need not be a variable, but it is, if you consider it an arbitrary element of your algebra, you know, it doesn't matter.
So if it's closed under substitutions, yes, that's unproblematic.
Well, anyway, I think, let's, since we are all tired, so maybe that question is just...
Yes.
I'll think about the question. I think I think it should be more or less trivial, but indeed...
Indeed.
I hope it is not. I hope actually it is not.
We just don't know which way, but yes.
Either it's trivial that, so I predict that either it's trivial that...
Yes, or trivial no, but it is...
You cannot.
I will keep hoping against all hope, but that will be a good excuse for us to actually get back in touch, Albert. Maybe even have it.
Yeah.
Okay. Yes.
Okay.
Albert is a well-known pessimist. Yes.
I'm an optimist.
In general, me too. But now I'm betting against my instincts. You know.
Okay.
Okay.
With this, I think it's time to finish. And
yes,
next time will be the lecture by Albert Visser on a topic which is on a joint work with Tadeusz.
Yeah,
but presumably a different one.
No, well,
really?
The non-circular graphs is not the joint work, but the
Okay.
work on the non-circular graphs is the joint work, but the circular graphs is
Yeah,
Okay.
that was an idea that Albert was pursuing passionately in recent months, and which took him away from our joint work. So I hope that this I hope that this idea fix will amount to something now.
But you can
But
come
yes,
to Albert's talk and take him back, so to say, to you.
yes,
Yeah.
yes. That's the plan. So you will see me forcefully trying to pull him back next week,
maybe
convincing him
discover a
that
fatal mistake. That would really help.
I hope that would that would help our collaboration, right? Because then you will have more motivation to return to other issues. So I will be a pessimist next week.
Okay. Thank you very much.